Hello everyone and welcome to another video. So today I want to talk a little bit about what's known as the matrix exponential. So for those of you who've been following along our discussion on ordinary differential equations, you know that we've started talking about state space and linear time invariant systems, which are basically systems of ordinary differential equations. Their solution is going to involve this thing called the matrix exponential. So what I want to talk about today is just a quick introduction to what is the matrix exponential. We'll give the definition of the matrix exponential, and then we're just going to look at some properties of the matrix exponential. We're going to save future discussions and analysis on this matrix exponential to separate videos, so I'm hoping that today's discussion will be actually pretty quick, because all we're going to do is really just introduce the matrix exponential, what it is, and talk about a few of its properties. So if that sounds fun, let's go ahead and jump right into it. All right, so let's start with the definition of the matrix exponential. And in fact, let's back up and we can actually even recall what's the definition of the normal exponential, right? If you just took this word matrix out, I think everyone knows what the exponential function is, right? It's e to the x, you know, sometimes you might see it written exp of x, right? And again, all of this is shorthand notation because mathematicians are lazy and don't want to write out the full infinite series definition of what this function looks like. Just to refresh your memory, right? This is a infinite series from k equals 0 to infinity of 1 over k factorial times x to the k, right? Okay, so in this case, let's consider the case where x is just a scalar, right? It's just a number, right? And if that's the case, this is the definition of what this function is, right? It's this infinite series. And you can plot this, right? There's no problem drawing this thing of x versus e to the x, or exponential of x, right? Everyone knows, you learned this in high school, that this thing looks something like this, right? It happens to go through the point 0, 1, right? And then it just basically starts blowing up and increasing exponentially fast, right? That's where it gets its name. So again, this is probably old hat. People understand what the exponent function or the exponential function is, but now I want to ask ourselves a situation of what happens if I tack on this adjective matrix in front of it? What does that mean? Well, it turns out that it's actually pretty close to the similar or same definition. If I now say I want to talk about e to the, let's call it capital X, okay? Or the exponential of capital X. And in this case, we're going to now consider capital X not to be a scalar anymore, but let's call it an n by n square matrix, right? What does this thing look like? What are we even talking about when you're talking about an exponential of a matrix? Well, luckily for us, the definition pretty much follows directly from the normal exponential definition. In other words, this is nothing more than an infinite series from k equals 0 to infinity of 1 over k factorial times x, big X in this case, the matrix x to the k, all right? So what does that mean? Maybe what we should do is let's write out a couple of terms of this. Let's start with a scalar one. I think everyone knows that the scalar term for this, if we were just to write out a few of these terms, right, it's basically what? It's 1 over 0 factorial times x to the 0, right? That's the k equals 0 term, plus 1 over 1 factorial times x to the 1, plus 1 over 2 factorial times x squared, plus 1 over 3 factorial x cubed, plus yada yada yada, right? Okay, so this all makes sense, right? Again, I think everyone remembers that this is just 1 over 0 factorial, this is just 1, and this is something to the 0 is 1. So this term, this first term, just becomes 1, right? Okay, so again, this makes sense. This is the infinite series. This is the definition of the normal exponential function. So now we can do the exact same thing for this matrix version of it, right? So the k equals 0 term of this is, again, 1 over 0 factorial times the matrix x risen to the power of 0, plus 1 over 1 factorial matrix x to the 1 power, plus 1 over 2 factorial matrix x to the 2nd power, plus 1 over 3 factorial matrix x to the 3rd power, plus yada yada yada, right? And again, this is very similar. The only difference is that now in this case, this is now the identity matrix, right? So this is, we're going to write this as I, and maybe I'll say I n by n just to make this explicit, right? And now the only thing to maybe think about now, this is pretty simple. X to the 1 is just the matrix X. But now this term and any of these other higher terms, all of these squares, cubes, to the 4th, to the 5th, all of these are matrix multiplies, right? These are not element-wise multiplication. Again, in a scalar case, we didn't make a distinction between matrix multiplication and element-wise multiplication, but now we have to be careful that in this situation, this notation where it's squared, you know, cubed, etc., this means, in other words, you know, x squared, this is really matrix multiplication of x times x, right? And x cubed is, again, matrix multiplication x times x times x, right? And again, this is where it gets a little bit complicated because you can't just multiply each element of the matrix and raise it to a power. You actually have to do the full-on matrix multiplication in all of these, and that's where the richness in this comes in, and we're going to examine that in a second, right? So, tell you what, let's look actually at an interesting example. All right, so let's start with an example of a diagonal matrix. And again, this adjective of diagonal is going to be very important, as you're going to see here in this example, as well as you're going to see later on down the road when we want to start talking about the matrix exponential in general. So again, I just wanted to preface this example with keep in mind this is a diagonal matrix, which is going to have some special properties here. So again, here's our diagonal matrix. I don't know, it just has 2t, 3, and cosine of t on the diagonals. And now we're asking ourselves, what is the matrix exponential of this matrix, right? So e to the capital X, right? Again, we said that is just an infinite series, as we discussed earlier, where all of these x squared, x cubes, these are matrix multiplications, right? So let's just write that out. So down here, I is obviously a 3 by 3 identity matrix, and then here's the first term right here, here's the second term here, and then again, I'm going to write these two as x squared being a matrix multiplication, right? Again, just to make it explicitly clear. And then I ran out of room to write the k equals 3 term, but I think you get the idea, right? Okay, so now let's go down one more line. So the identity matrix stays the same, this term stays the same. Now this one, what makes it really interesting for a diagonal matrix multiplication, right? With a diagonal matrix multiplication actually is the same thing as element-wise multiplication, right? Because if you do the math, right, and you do the matrix multiplication, this is going to multiply with this, that's going to multiply with that, etc., right? So you end up with basically this expression down here, right, where it's the same as element-wise operations. And again, I want to stress it one more time, just in case we missed it earlier. This is only for diagonal matrices. That's the only time you can treat matrix powers as basically element-wise powers, as you see here, right? Okay, so what makes that nice, right, is now let's just add all these matrices together. So for example, in the 1, 1 element, you have a 1 plus 1 over 1 factorial 2t plus 1 over 2 factorial 2t plus 1 over 3 factorial, 2t squared. You get what I'm saying, right? You only get the 1 entries, right? So that's what this is here, right? This, zeros, and then in the 2, 2 element, you also pick up the 1 from here, the 1 over 1 factorial 3, the 1 over 2 factorial 3 squared, etc., right? And again, same thing down here, and you get a bunch of zeros until you end up with the 3, 3 element where you pick up the 1 over 1 factorial cosine t, the 1 over 2 factorial cosine t squared, the 1 over 3 factorial cosine t cubed, etc., right? So if you stare at this long enough, you realize, hey, there's zeros everywhere, and then there's just an infinite series on the diagonals, right? And if you look at this infinite series long enough, you realize that it's just this, right? 1 over, from k equals 0 to infinity, 1 over k factorial times 2t to the k, right? Etc., And then, again, if you remember, this is just e, right? The e is the lazy way to write this infinite series. So really, at the end of the day, here is the matrix exponential, e to the capital X, right? Here is our result. And again, let me stress that this is a diagonal matrix, capital X, right? So what is fascinating about this case of the matrix exponential is if your matrix is diagonal, the matrix exponential of a diagonal matrix is just you exponentiate each diagonal element, right? And again, I'm not sure if that's an actual real verb, but I think you get what I'm saying, right? you basically just raise each diagonal element to e to that element, right? And that's what you end up with. Now, again, this is only for a diagonal matrix, but we are actually going to leverage this fact in a couple of videos when we talk about calculating the matrix exponential for a general non-diagonal matrix, and we're going to see that this actually is going to come into play, okay? The other thing that might be interesting to mention is, okay, let's talk about the general non-diagonal case, right? There are plenty of situations where this shows up. So Mathematica, you might run to a computer tool like Mathematica to calculate it. It has a function called matrix exp, which will allow you to do this. So if you go ahead and plug in this matrix into Mathematica and send it to the matrix exp function, and I'll show you a screenshot of what it looks like, and you can see you get that result, right? Where you have a diagonal matrix. If you want to calculate the matrix exponent of it, it's basically just taking e of all of the diagonals, right? Now, here's the case of a non-diagonal matrix and then sending it over to Mathematica and calculating the matrix exponent using matrix exp, right? And again, you can see from this situation that there's something clearly more going on, right? This is the matrix exponent is not simply raising each element to e to that element, right? It's something much more complicated. And in fact, that's what we're going to get into in future videos. But I just want to point this out to you right now that this property of using a diagonal matrix, it's super duper easy to calculate the matrix exponent, right? Now, why don't we take a moment now to actually talk about some other properties of this matrix exponent. All right, so let's look at some properties of the matrix exponential, and we're going to see that a lot of these have parallels with the standard exponential. So let's look at some standard normal properties first. So if you are raising a zero matrix of size n by n to the matrix exponential, or you're going to take the matrix exponential of that, it basically is the identity matrix, right? So this is very similar to how e to the 0 equals 1, right? Okay, how about this? What if you want to take the transpose of a matrix and then calculate its matrix exponential? Well, it turns out that's the exact same thing as calculating the matrix exponential of the matrix first and then transposing it, right? That happens. What if you have the product of two matrix exponentials where you have little a and little b, which are scalars, right? And then capital X is, again, your square matrix that we talked about earlier. Well, that's the same thing as the matrix exponential of a plus b times the matrix x, right? You compute this entire new matrix and then take its matrix exponential, right? Now, here's an interesting one. If x and y, these are both square matrices, if they're commutable, meaning if x and y is equal to y times x, right? And again, that's not always the case with matrix multiplication. There are plenty of counterexamples where this doesn't hold. But if it does hold, then you can basically do this, right? You can take the two matrix exponentials, flip around the order of either, or you could take the sum of the two matrices and then take its matrix exponential. So again, these are some interesting matrix exponential properties. But now let's talk about some that are actually going to be very useful for our study of ordinary differential equations. So the first one I want to look at is this so-called derivative property of the matrix exponential. So let's say you have some matrix exponential here, e to the a, and let's say that the thing that you are raising to the exponent is a function of time, right? So in this case, the matrix, it's some matrix a times t. So I just want to introduce a independent variable into this case. Let's say you want to take the derivative of this matrix exponential with respect to the independent variable, in this case t, all right? Okay, well, let's work this out. Let's just write this thing out. So again, the matrix exponential of e to the at, that's just, we can just write its identity right here. It's just the infinite series 1 over k factorial times at to the k, right? And then I want to take the time derivative of whatever this thing is, right? This giant infinite series. Well, tell you what, let's write out this giant infinite series. We'll write out 4 terms here. Okay, and now it's very clear that I can take the derivative of this first term, plus the derivative of this, plus the derivative of this, plus the derivative of this, plus the derivative of that, et cetera, right? So that's all I'm doing down here in this next line, right? So you can see the time derivative of the identity matrix. Well, I don't see t in this identity matrix. It's a constant, so its time derivative becomes 0, right? Now, let's take the time derivative of this term, 1 over 1 factorial times at. That's really easy. It's just 1 over 1 factorial times a, right? The t goes away. How about this second one, all right? Now this one, obviously you can see that we've got at kind of here inside the squared. So this becomes 2at, and then from product rule, I got to pull out an a on this side, right? So here's the derivative of this term. And then same thing over here. Whoops, sorry, that 3 is in the wrong spot. This cubed should be on the outside, like this, right? Because now I take the derivative of this entire term, so I get 3at squared, and then one more a pops out due to the product rule. And same thing over here, right? Now, what's fascinating about this is if you look at this, for example, right here, you got this term 1 over 2 factorial times 2, right? That's this little bit right here. Well, if you think about this long enough, isn't this is the same, what's 2 factorial? It's 2 times 1, and then I got to multiply by 2. So this cancels, so this is actually the same as 1 over, you got to write this as 1 over 1 factorial if you want, right? So this bit here, maybe I should circle it in a different color, right? This little bit becomes 1 over 1 factorial, right? Now, let's look at this thing. Right here. What is this thing? 1 over 3 factorial times 3, right? Well, again, let's write out this factorial. This is 1 over 3 times 2 times 1, whoops, times 3, right? Again, these 3's cancel, so this is the same thing as 1 over 2 factorial, right? So this blue little bit becomes 1 over 2 factorial. And same thing, 1 over 4 factorial times 4 is the same thing as 1 over 4 factorial. And you can see where this pattern is going, right? This just continues on and on and on and on, right? Now, what's interesting is if you stare at this expression now, this one right here, you see that there's an A, an A, an A, an A. And in fact, if you wanted to, you could expand this AT squared and you would basically get a whole bunch of A's. And what I'm trying to get at is you can now factor out an A in either on the left side, as we've done here, or you could also do it on the right side, right? It's kind of arbitrary which side you want to pull the A out on. For this example, let's pull it out on the left, okay? So if you pull it out on the left, you go from here to here, right? So this A becomes an identity matrix, right? And I'm pulling out this A out on the left, so this just becomes this term, right? 1 over 1 factorial times AT, et cetera, et cetera, et cetera, right? Now, stare at the thing in the brackets. This should look really familiar, right? It's this infinite series, which again should look really, really familiar, right? That's just e to the at, and then I got to have this a in the front, right? So really, at the end of the day, this here is d dt of e to the at. Right? And again, remember, in this example, we happen to have pulled the A out on the left. There was nothing stopping us from pulling this A out on the right, right? I could do that as well, right? And in that case, this would become like this, right? And then this actually becomes e to the at, right? That's this thing in brackets, and then the A comes out on that side. So here is our end result, which is really fascinating and will turn out to be useful. And you can kind of see that, again, it's similar to how a normal exponent works, right? If you had e to the lowercase at, right? If these are just scalars, right? And you take its time derivative, I think everyone would agree that this is just a e to the at, or you could put this a on the other side if you want. And for scalars, it doesn't matter how you want to write this, right? It's just we see the exact parallels show up in the matrix exponential as well, due to this process, right? So this is another fascinating property of the matrix exponential when we're talking about taking time derivatives. And again, I just wanted to go over this in a little more detail because we will be using this fact a little later on down the road when we start investigating ordinary differential equations, okay? All right, so let's erase the board and look at one more property of the matrix exponential. All right, so the next thing I want to talk about is how the matrix exponential is related to similarity transformations. And remember, we had a completely separate video dedicated to what a similarity transformation was for matrices. So I would encourage you, if you're interested, to feel free to check that video out if you want some details. But really, long story short, all a similarity transformation is you basically take some matrix and then you multiply by P inverse and P. This is some invertible matrix, and you get another matrix, right? All it does is it allows you to maintain properties about one matrix while kind of expressing it in the form of another matrix, right? So that's all this is doing, right? If you want, you can just think about this as just an equation, right? A tilde is equal to P inverse AP. It's a matrix equation. So let's say that you want the matrix exponential of A tilde, right? Well, since we know that they're related through this similarity transformation, I can just write, okay, A tilde is the same thing as P inverse AP, right? Okay, so the matrix exponential of this thing, it's basically this infinite series from k equals 0 to infinity of 1 over k factorial times whatever is being exponentiated to the k, right? That's all this thing is. Okay, let's write out a few of these terms like we did before. So here's the first 3 terms. And now what I want to do is draw your attention to things like this thing, P inverse AP squared. That's the same thing as P inverse AP times P inverse AP, right? That's all it is. It's this matrix times this matrix, right? In matrix multiplication fashion. And same thing, this thing right here where it's this, you know, it's a triplet of matrices, but whatever, is raised to the 3rd power. It's just this matrix times the triplet of matrix times the triplet matrix, again, 3 times in a row, right? That's all this is doing, right? Okay, now what's interesting about this is if you think about this, I can erase these parentheses right here, right? This and this can be gone if we want. And then same thing, let's come over here to this 3rd term. I can erase this this parentheses, those don't do anything. Same thing, these don't do anything, right? And now what's fascinating about this is if you look at this, we end up with P times P inverse sitting here, right? This basically turns into an identity matrix, or we can just not write it, right, if we wanted to. Same thing, right here, you got a P times P inverse. That thing goes to identity matrix, and then same thing, you got another one right here. This is another identity matrix, right? So this line can actually be rewritten as identity matrix plus 1 over 1 factorial P inverse AP plus 1 over 2 factorial. Now this time we end up with what? P inverse, and then this A is going to be next to this A, so I could write that as A squared, right? And then I end up with a P on this side, right? Okay, and then plus 1 over 3 factorial times this thing. What do we end up with here? This is, we got the P inverse, and then this A, this A, this A are all next to each other. That's the same thing as A cubed, right? And I have the P on that side, right? Plus yada, yada, yada. You'll see this pattern just repeats and repeats and repeats, right? Wait a second. Did I, 1 over 2, something looks fishy right here. What did I do here? Identity P inverse AP. That should, oh, this is my sloppy plus sign. Sorry, that's why this looks ugly. Okay, great. Now, let's play another trick, right? This identity matrix, can't I just rewrite this thing as identity matrix is the same thing as P inverse P? Would everyone agree that's still the identity matrix, right? And now, the beauty of this is, look at this. On the left side, there's P inverse on this term, P inverse on this term, P inverse on this term, P inverse on this term. So you know what? Let me pull off P inverse on the left, right? Okay, and then the other thing, look at this. On the right side, there's a P, a P, a P, a P, and this is going to keep going on forever, right? So I could just pull off the P on the right side. What am I left with in the middle? I'm left with, okay, this thing when I pulled off the P inverse and the P, this is just the identity matrix, right? That plus 1 over 1 factorial P inverse A P plus 1 over 2 factorial P inverse, oh, no, sorry. Ha. Oh, excuse me, I'm choking on sneezing on this dust here. Sorry, I pulled off the P inverse, right? So this is just A here, right? And I pulled off the P on the other side, that took care of that. So this is plus 1 over 2 factorial A squared plus 1 over 3 factorial A cubed plus yada, 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 right? Does everyone see? And now, look at this. This is just that infinite series, right? So this whole thing just becomes P inverse times the infinite series from k equals 0 to infinity of 1 over k factorial. Then what do we have? A to the k, right? And then you get the P on the other side, right? And again, this whole thing, the lazier way to write that is just the matrix exponent of A, right? So here is our result, right? The matrix exponential of P inverse AP, or the matrix exponential of A tilde, right, that we started off with, is this. So this P inverse and the P, they sort of fall off to either side, and you can now, what you can end up doing is if you want to calculate the matrix exponential of this triplet, right, you actually only need to calculate the matrix exponential of e to the a, and then you can just pre-multiply by P inverse and post-multiply by P, right? That's what you end up with, right? Again, this is incredibly helpful, and again, I want to draw your attention to this, and maybe here's a little bit of a sneak preview, and maybe tying it back to what we talked about earlier, is think about what if this thing was non-diagonal, right? It's some general matrix, an n by n matrix, where it's tough to calculate the matrix exponential. But what if you could make it so this A here was diagonal? Right? And again, I think you're starting to see the bits of this. In fact, we will talk about this in detail when we go in our separate video where we talk about how to calculate the matrix exponential using what's known as the modal technique, which actually makes explicit use of this property, right? Okay, so I think that's enough. Tell you what, let's jump over to the computer, and these last two properties were so important, I think it might be useful to kind of illustrate how you might do these in, say, Mathematica if you want to check that they're actually true. All right, so here's the same non-diagonal A matrix that we were looking at earlier. So let's go ahead and first check that we have the property of, if I have e to the at and I want to take its time derivative, we should show that that's the exact same thing as a times e to the at, or e to the at times a, right? Okay, so the first thing to do is let's go ahead and calculate just plain old e to the at, and let's using Mathematica's matrix exp function, right? So we can do that by just calling matrix, exp on a times t, right? Let's assign this to a variable. I'll call this maybe EAT, right? Okay, so that's what that matrix looks like. And again, maybe what I'll do is let's do it like this. Let's show this as a matrix so you can see that more easily, okay? And now what we can do is let's calculate the time derivative element-wise. What I mean by that is let's just take the derivative of this first term and the derivative of the second term, the derivative of the third term, the derivative of the fourth term, etc., right? In other words, what we're going to do is we are going to calculate manually this left-hand side, okay? This thing, okay? And maybe let's call this another variable. We'll go ahead and do this first. So take the derivative of EAT with respect to t, and let's call this, I don't know, d EAT with respect to dt, right? Something like that. Sorry for the variable namings, but I think you kind of get what I'm doing, right? Okay, let's go ahead and look at that. So here you go. Here's the time derivative of this. So you could either do this brute force like we showed here, or let's go ahead and show that this is true, okay? So in other words, let's go ahead and calculate this thing, a times e to the at. So a dot EAT, right? Or I guess to be fair, we could do this, matrix exp, if we want to do this completely by hand, right? This is, let's call this, I don't know, let's call this term 1 or something like that. Let's call this, how about term 1? And then term 2 is just the exact same thing, but we are going to post multiply by a instead of pre-multiplying by a, right? Okay, so those two things, term 1 and term 2, should look the same as this time derivative that we calculated manually. And they do look pretty similar. In fact, if we want to double check this, let's just go ahead and say this, does this equal term 1? And does this, whoops, come on, paste, equal term 2, right? Just to have Mathematica check it for us. And yes, it says true, true. So there you go. At least for this case, we definitely showed that this property is true, right? Okay, how about the similarity transformation? If I could spell this, similarity transformation, right? Check. Let's go ahead and check that right now. So let's go ahead and make up some P matrix, right? So I'm going to make some non-singular transformation matrix P. In fact, if we want to see this, we can look at this, yeah, we could look at its matrix rank, right? And we can see that it's 2. Yep, it is 2. So this is full rank, so this is invertible. So we should be able to provide a similarity transformation. So what I want to check now is we want to make sure that the property we showed earlier, namely e to the p inverse AP, is the same thing as p inverse times matrix exponential of just a times p, right? So let's go ahead and calculate the left-hand side of this, right? So this is the matrix exponential of p inverse dot a dot p, right? So that's the left-hand side. And then let's just look at it. Okay, and then let's calculate the right-hand side. That is inverse p, right, dotted with the matrix exp of a dotted with p, right? So that's the right-hand side. right? And again, let's just check that the left-hand side is equal to the right-hand side. So, whoops, what the... Oh, sorry. INV is, that's like the MATLAB speak. I need to type out the full inverse like that. There we go. And it doesn't look the same, but I think that's because we probably should have simplified the right-hand side. Let's try it. Let's put a simplify on both these. Okay, there you go. Now they look the same, and again, it does check out to be true. So again, in this case, we showed that this holds, at least for this specific matrix, and given the proof that we showed on the board, this should hold for pretty much any non-singular in similarity transformation P. All right, so there you have it. Like I said, I wanted to keep this particular video somewhat short and just introduce the idea of the matrix exponential. The reason being, in our immediately following 3 videos, we're actually going to have additional discussion on this. In particular, I want to first talk a little bit about how this matrix exponential is going to help us in the context of solving linear ordinary differential equations, specifically linear time invariant state space systems. And then with that information and context in our mind, we can actually talk about practical ways to compute this matrix exponential, particularly in the context of linear ordinary differential equations. So we'll look at 2 additional ways that you can actually compute this for general non-diagonal matrices. So that's our plan of attack for the next several videos. And with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you click on that subscribe button, it really does help me continue making these videos, and I hope to have these videos out fairly soon. And remember, the new ones come out every single Monday, so I hope we'll be able to catch you at one of these future discussions and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.